they like part of the? Oh, I think they are part of the. Yeah, it works. High enough, right? I guess you can always use this as like criteria.
That's fine. All right, welcome back, everyone, for our last lecture of the day, and our fourth new lecture of the week. So I'll turn it over to David to introduce her.
All right, very good. So our last lecture of the day and the last lecture of this week is Irene Valenzuela from CERN and IFT Madrid. And she is going to tell us all about the Swampland distance conjecture.
Okay. Thank you very much. Of course, thank you to the organizers for the invitation, and thank you, all of you, for staying until the last lecture of the day. So, I imagine that you are tired, as I am. Well, probably you are more tired than me because you've been already, like, this is the third week or the fourth? Third week. Wow. Congratulations. So, I will try to make it, I don't know if to say entertaining, but not too boring, let's say. But I think the best way to keep yourself awake, and probably also myself awake, is that you ask questions. Okay, it's a trick. So don't hesitate to ask, to interrupt me. I'm very happy to stop. We'll see how much we can say. The goal here is that the message gets across. So if there is anything that is not clear, I mean, you come all from different backgrounds, so don't feel stupid or anything like that, okay? If you don't understand anything, just say, hey, I haven't seen that, okay? Good, clear? Good. Okay, so the plan for these lectures is to give you, well, what is some more modern or current understanding of the Swampland distance conjecture, okay? So I'm going to focus on one thing, let's say, of the Swampland program, which is central idea, and has many connections with many other different things. Because I think it's a great excuse also using this distance conjecture as a common thread to learn about different topics in string theory and quantum gravity. So we'll use this to learn about string theory, duality, compactifications, these type of things. We will also learn about CFT conformal manifolds, okay, in area CFT. And of course, I mean, you'll learn a bit about what's the Swampland about and how we can use it, okay? So the plan for the 4 lectures, I'm gonna start with basics of string theory and dualities and this type of thing. So here is where I also need your input, background knowledge. We'll use this to motivate this distance conjecture, this criteria. And then I'm gonna go deeper into understanding how it's really realized in string theory in various examples. First, in Minkowski, okay, in flat space. And then I think the third day, it will be completely focused on area CFT, okay? So we are gonna see how this constraint gets translated to a very concrete statement on conformal manifolds that one can aim to prove, okay? So here, what I will tell you about is recent developments of the past 2 years, okay, 1-2 years, okay, where this is very quickly evolving. So here we already have some partial proofs for this statement, and it's a matter of time, okay, I think, to get the final proof. So this might become a theorem, at least in area CFT. And other backgrounds is more difficult, but at least here, so I want to tell you about this. And then finally, the last day, it's the last day, we'll be very tired at the end of the week, even more than today. So I will have a more fun lecture, okay? I mean, we'll see, okay, the things that we have learned, what are the implications for the universe, okay? We can give any constraints for phenomenology, and then we'll connect to other Swampland criteria, okay? So using this statement, I will connect with other that you might hear. I mean, maybe you hear in other lectures or conferences. So If you get lost at some point here, don't worry. I mean, because this is very different Minkowski from CFT, so it will be different, very different lectures. And if you get lost in the three of them, don't worry, you can come to the last one, at least have some fun about implications. Okay, so before I start, let me ask also, well, two things. Once, I guess it's common to write the touchy lectures afterwards. I haven't started typing this. Plan to do it. I will put you, I think, on this platform, right? Like the references and this type of things. There is one, I mean, I have some lecture notes from the past, like 5 years ago, which, I mean, some things are useful, others are completely new, so you will not find there, but okay, this is one reference you can take now, and I will put more references, okay, in these files. And then, so what I was gonna say, so for these lectures, I'm looking actually for volunteers. If any of you want to help to type the lecture, if I'm allowed to do that, I mean, it's fine. You can help me, so you are also a co-author, okay? So it's completely voluntary. It's a way to learn more about the topic, an easy way sometimes to get citations. So here I did it with other students as well. I think it's his most cited paper, so I don't know if it counts, but anyway. So yeah, keep it in mind. I'm saying it now so that if you are interested, you can already start paying attention, okay? I'm taking notes, but anyway, you can just tell me your name. If there is more than one person interested, I will probably just choose randomly, just let me know. Okay. Good. And the other thing, so I wanted to gauge a bit your background knowledge also. So here, let's start more basic. So who has had at least one course in string theory, like thinking of superstring theory and maybe toroidal compactifications of superstring theory, this type of things? Raise hands. Okay, half, probably half. Who has had no course of string theory at all? Good, people. Okay, well, it's fun. You will learn some things, I hope. Who has no idea what's the Swampland program? Has never heard anything? Okay. Actually, there are less people aware of what's the Swampland program that has had a course in string theory. It's crazy how things change. Okay, good. Okay, so that's for me. So let's start. This one, right? Yeah, it's better. Also, is it okay, this size of, like, it's big enough? Just to check. Good? Okay. If I fail, let me know. I will probably fail at some point. Okay, so let's start with some intro. I mean, even if, like, most of you have already heard something about the Swampland program, I mean, cannot start without saying at least a few words. It's for the 4 or 5 people that never heard about it, okay? So the goal here, okay, now I have to write bigger, is the space of UV consistent gravitational EFTs. So EFT is effective field theories, okay? So the goal is if you have some effective field theory that is coupled to gravity, what are the constraints that this EFT must satisfy so that can be UV completed in quantum gravity, okay? You can ask the same question without the gravitational here, just purely, right, in field theory. We know there are constraints even there, right? Like not everything can be UV completed. But in the Swampland, we really care about theories that are coupled to gravity, okay? So just to be clear, if I have some effective field theory, so with an effective field theory that is weakly coupled to gravity, so here I mean like general relativity, okay, less than gravity. So we have some rich scalar, some matter theory, and then many, like an infinite tower of non-renormalizable operators, right, that are suppressed by a cutoff, okay? So the question is, can I put anything here and here? Or are these things constrained? Okay, so that it can be embedded in quantum gravity. That. It's very important and effective field theories, okay? So these are always defined up to some cutoff, okay? So this lambda of the theory, okay? So it's a low energy description. And we are also interested in the Swampland and understanding what is this cutoff in practice. Okay, can we say anything about, when, like if I have some effective field theory weakly coupled to Einstein gravity, what is the scale at which Einstein gravity breaks down? Okay, and I need to go really to a quantum gravity theory. Okay, is this correlated in any way with what we put here or not? Okay, so in this course, in these lectures, okay, the main question we are trying to learn about is precisely what is this cutoff scale. Cutoff scale lambda. Okay, can you read here? Maybe I stop here. Okay, let me just write this, at which Einstein gravity breaks down. Okay. Okay, if I just ask you this question, what would be your naive case? The Planck scale, right? At the very least, right? We expect that Einstein gravity is going to break down at the Planck scale, which is very high in energies because gravity is very quick in our universe, right? But I will convey in these lectures, and it's one of the lessons we have from string theory, is that sometimes, okay, it depends on what you put here, what limit what is the type of effective field theory you are considering. This cutoff can be lower than the Planck scale, okay? Okay, sometimes, and that's what we'll try to define carefully, okay? We put now sometimes, okay? So that the scale at which the Einstein gravity exclusion breaks down can be much lower. For instance, string scale can appear at a low energy scale, okay? And this is something which actually, as I said, gets correlated to this, and it's interesting for phenomenology because, right, like when you work in phenomenology, you are very interested in understanding what is the scale of new physics, right? So if we can get some recipe about what's going to be the scale, depending on what you put here, it's not only about ruling out, it's more about informing, okay, models for particle physics and cosmology. Okay, so this is one of the main questions we are trying to answer. Good. Okay, let me continue here. Now, how we do that? How? Well, here, the Swampland program, we work with a combination of this top-down data from string theory okay, so we take all possible compactifications we can think of, string theory, study different models and so on, and try to learn if there is anything sort of universal about this that is satisfying all the models, or everything is just model dependent, or what's going on, okay? If there is any general lesson that we can extract. Okay, so, of course, the goal is to understand the constraints from quantum gravity, but at the moment, this is the best, I think, framework that we have that is concrete. So here we can be very quantitative, very sharp, and it's what we use to extract lessons. Okay. Now, the whole goal is try to understand whether these lessons are universal or not. So we have to move also beyond string theory. And then this has to be combined, okay? So with bottom-up arguments. Independent of string theory, which might rely on the physics of black holes, or more generally, like not on concrete models, but on holography itself. Scattering amplitudes. In the past 2 years, I mean, there is actually a lot of correlation now, as you can imagine, with the bootstrap program, both the S-matrix bootstrap and the conformal bootstrap, because in a sense, we are trying to answer the same question, right? What is the space of consistent quantum theories? So, I mean, we start getting intuition from string theory, and then we try to find these arguments. In the bootstrap, you try to go the other way around, actually, right? Like it's more like bottom-up, like I just impose some things about the UV, like unitarity or causality or things like that, and then I see what I get. But then the two programs are gonna cross, right, at some point. And there is actually many, I mean, I will tell you in the context of ADS-CFT, there has been very nice developments precisely from the interplay, okay, between these two approaches, these two programs. Okay, so if someone, I mean, in general in the community, like, I want to remark it's important to have both things, okay, because this is what allows us to be very quantitative sometimes, but this is what allows us to understand if it's model dependent or not, okay, if it's a universal feature or not. And then just to finish this, and you make the typical picture, so you will say many times, but just feel bad if I don't do it. So sometimes the way we represent these Swampland constraints is to say, okay, imagine that you have some space of effective field theories, which is the landscape, okay? These are the ones that are UV consistent with quantum gravity, okay? So that's if I have here some energy scale, somehow they arise as low energy limits of a quantum gravity description. And the point is that this effective field theories is only a subset of the full set of infinite effective field theory that you could imagine to construct. And if you don't satisfy these constraints, then you will say that the theory belongs to the Swampland. Okay, so these are not consistent with quantum gravity, and these are consistent. And we typically draw a cone precisely because the constraints that you get are correlated to what is this cutoff. In the sense that if you want your theory to be valid at higher energies, the constraints are stronger. If you want it to valid only at very low energies, the constraints become weaker. Okay, any questions so far? Yes? Yeah, that's part of the question. I mean, it's part of the question of the program itself. Sorry. So he said, he asked, when I say quantum gravity, do I mean string theory? Right? So this comes here. Okay. We start with string theory, so yeah, for sure I mean string theory. But then the question is, could it be even more general than string theory for other quantum gravities if they exist? Okay. Sometimes when you have this type of arguments and you have an argument for that, it makes you believe that yes, maybe it's beyond that. But it's part of the program to try to find out that, right? I don't have another way to check if it's more universal string theory, more than these arguments. But this is actually, I mean, it's an important thing. Like let's talk about it. But they are part of the community in the Swampland program is focused in this string universality question, or string Lamport principle, whatever, which is precisely trying to understand, okay, how universal are these constraints beyond string theory, in the sense of, can I, like, if I have, imagine that here I put string theory, really? And if I have a theory here that does not arise from string theory, can I somehow be convinced, or can I argue that there is really something sick here that could not arise from some other quantum gravity theory? And then can I show that everything that is consistent actually arises already from string theory? That's why it's a string universality. This has been shown, like, I mean, last day I might tell you something, but if you just assume no global symmetries, that, okay, it's something we'll discuss at the last day only, you can show that all effective field theories that do not have global symmetries with dimension bigger than 6 and 16 supercharges or more already belong to the string landscape. So in that sense, there is string universality there. But more questions? Okay, so enough with the intro. Let's move this here. Okay, so let's start basic. Let me also, maybe I should have said, of course, this name of Swampland comes from Conrad Baffa in 2005. Although this program only really took off in 2015. Okay. The last day I might tell you more about this, because it's actually quite fun how it started. It was because of an experiment, because of biop, okay, that triggered this whole revival of the Swampland program, which has quickly evolved since then. As I said, like many of the things I'm going to tell you are of the past 2 years. And the reason was that it was kind of that arose as a counter reaction to the amount of, I don't know, like supergravity models, okay, that were constructed to explain these experimental results that in the end were wrong, the experimental results. So it was like a step back of the community, like saying, okay, maybe, I mean, because this was, I mean, because you can imagine, but probably you saw it last week with Liam, right? Like try to construct a model that resembles the universe is very hard. Okay, it requires a lot of technical work. It's very valuable, very hard to do. So there was a point, I mean, not right now, but in the past, in which the people were not so motivated, and then people that still were trying to construct models that resemble the universe, then were working more like on supergravity only, without talking about string theory, but still calling the models string theory models, many things. So there was kind of a counter-reaction of, okay, maybe let's try to be more careful about what we say really comes from string theory, like try to be more critical with the models, with everything. And by doing that, I mean, let's like trying to take a step back and say, okay, let's focus on things we know, we understand, we control, and see if from that we can extract some general features and understand whether they are really general or not. Okay. But we'll see about this experiment on last day. Okay. So, as I said, I'm gonna center the lectures into around this question: what is this cutoff? Okay. So what can we? I mean, let's start from basics of string theory. So what can we learn about this UV cutoff from string theory? Okay. Is there anything, if any, no, that we can say? So right now I'm really going to focus on the string theory.
A quick question.
Yes.
You said, could you just say a little bit more about the result? I thought you said if we assume no global symmetries, then any BOT and D larger than 6 has a string coefficient. Is that right?
Yes, okay. With a very supersymmetric. Okay. 16 supercharges or more. Okay. This is this is something recent of the past few years. Like you can, and it's no global symmetries in a generalized sense, like take into account topological symmetry, generalized symmetries, categorical symmetries, like all this type of new types of symmetries. And then you can show that, I mean, these highly supersymmetric theories are, you can try to classify just in terms of the rank of each group and very few data. And then you can show that those that do not arise from string theory actually has some sort of global symmetry. So if you think that there are no global symmetries in quantum gravity, that gives you the string universality. Yep. Okay, any other question? Good. Okay, so what can we learn about this cutoff? Well, so let me gonna say three things. So the first thing, okay, when we have we have a string theory at low energies, okay. Well, when it can have, it admits some Einstein gravity description, okay, coupled to matter. And the first thing, one learns from string theory is, I want to be clear, is that all the parameters, so if I have here, okay, in this L0, okay, so it depends on masses of different fields, so we put masses, couplings, gauge couplings, different things, okay, so here are many parameters of the EFT. So one of the things, right, we learn from string theory is that these parameters are not random parameters. Like if they are continuous parameters, they are given by the vacuum expectation value of scalar fields, okay? In the sense that there are no free parameters in string theory in this sense. So all continuous parameters and scales with respect to the Planck scale in Planck units, let's say, are set by vacuum expectation values of scalar fields. Okay. Okay, fine. Okay, is this clear for everyone? Let me give you an example. So, if I have, for example, 10D string theory, in 10 dimensions, if we have 32 or 16 supercharges, we can classify the possible worksheets that we have, right? So let me consider, like the typical string theories, like supersymmetric string theories with 32 supercharges or 16. So this is A to B or A. This has 32 supercharges, or heterotic type 1, okay, which has 16 supercharges. Okay, so this is the complete landscape that we have. If you write in 10 dimensions the effective field theory at low energies, right? This, I hope this is familiar for the people, but otherwise, since some people didn't have string theory course, let me say. You have the Einstein term. You have scalar. So I'm going to write always everything in the Einstein frame, okay? Which means there is nothing in front of the Einstein term. So this S is a scalar, which is the dilaton, right? 1 over GS. Okay, that was play a very important role in Henry's lectures. Okay, so it will also be important here. And then you have different like P4 gauge fields, generalized fields, right? From the Nevers-Bar sector, the Ramon-Ramon sector, and all these couplings are just parameterized by the dilaton, right? So you have the Nevers-Bars, which is common to all these string theories, and then you must have, like, if we are in type 2, you also have the Ramon-Ramon sector, right? Ramon-Ramon fields with different couplings depending on which one, that also are parameterized by the dilaton, and different Chern-Simon terms, and so on. Okay? But the message I want to remark is that, yeah, there are no free parameters in the sense that when you write everything in Einstein frame, all parameters are fixed by the dilaton in 10 dimensions, which is the only scalar, non-compact scalar that we have. Okay? Here, sorry. This is huge. Hello. Okay, so entendí only one non-compact scalar. Dilaton, okay? Yes.
What about alpha prime?
So that's why I'm writing everything in Planck units. So the string scale, right, alpha prime, in terms of the Planck scale, is also fixed by the dilaton. So any scale that you have in Planck units, it's fixed by the scalars. Okay? You can choose, I mean, in the end, what is physical are the ratios between the scales, so you can choose what is your reference unit. Could be alpha prime, or it could be the Planck scale. Here for the Swampland, we always choose the Planck scale, okay? Because then we connect with phenomenology and so on. Good. Okay. Yes, we are gonna build up everything, okay? So from very, I mean, I hope more basic things to more complicated, okay, compactifications.
What is the second term there? It's partial S.
Here, yes, sorry, this is the derivative. So I just mean the kinetic term for the scalar.
Oh, that has a S square in the over this different frame. Has a S square up.
Square. This is the derivative of the dilaton square. I'm just writing the real scalar, so that's it. With a metric, which is 4 times S square. Okay, so in 10 dimensions, if you write effective action, okay, that's what you have. So that's why it's a scalar, in this case, is a massless scalar because it only has a kinetic term. Good. So just to, yeah, these are like different kinetic terms, let's say, for the different gauge fields and so on that you have, everything parameterized by the dilaton, okay, just as an example. Okay, so since it was asked, let me also remark. So here, I mean, the question we're trying to answer is what is the cutoff scale, right? So what is the cutoff scale for this action? Okay, so this is an effective field theory action, supergravity action, in 10 dimensions, in which I am actually only writing what are the 0 modes, right, of the whole string spectrum. So here you have plus, right, all string modes, excitations. So if you just write effective field theory with the 0 modes, this is gonna break down at some scale, which scale is this breaking down? Planck or string? String scale, okay? So here, the cutoff of the CFT is not the Planck scale, it's the string scale, right? Because at the string scale, okay, so this supergravity, okay, this sugra action, sugra EFT, is valid up to some cutoff, which is the string scale, because at that point, you start, I mean, if you want, you would have many higher derivative corrections, which get important at the string scale. You have to integrate in all the string modes and so on, and then there is no quantum field theory description anymore. That makes sense, right? You cannot continue talking about a quantum field theory description coupled to Einstein gravity. You really don't need to go to string theory. Okay, so the scale, okay, this is the scale at which, let's say, a local QFT description coupled to gravity breaks down. And here we need to go to quantum gravity, we need to go to string theory. Okay. Now, this string scale, right, so we said, it's actually related to the Planck scale, also by the dilaton, okay, which is the only the scalar that we have. Okay, in such a way that, of course, if the dilaton becomes very small, no, the scale goes down in Planck units. So far, so good. I'm not saying anything, right? Everything clear? Okay. Okay, so this lambda, let me be clear, depends on the scalar, okay? Let's call it, no, I call it S, right? Okay, depends on the scalar of your theory. Okay, this is one of the lessons we have, but we can be more precise about this. In the sense that, I mean, what we have here is some scalar manifold. In the sense that, I mean, you can think of all the F, right, parameterized by the different scalars. In this case, it's only one scalar, so it's a one-dimensional scalar manifold in which you can put some metric on the scalar manifold, which is precisely the metric of the kinetic term, right? So it has a metric, which is 1/2 square, right? Appear there. So we can measure distances in this manifold. So a geodesic distance, I mean, because I'm doing this to find a notion which is independent, like different invariant, so it's independent of field redefinitions and so on. Okay, so what's something that is a good notion is to talk about a distance, okay, which is just the integral taking into account the metric, say the Val-Peterson metric. So if you take this metric, which goes as 1/2 square, the distance goes logarithmically in this dilaton, right? And this is what we call like a scalar canonically normalized in Planck units in Einstein frame. Okay, so if I write this kinetic term, right? So I had, right, derivative of s squared over 4s squared, right? So in terms of this phi, this is just 1/2 d phi squared. Okay, so for people that work in effective field theory and so on, this is what they call a canonically normalized scalar, which is just to talk about the distance in the scalar manifold. Okay, so in terms of this, what happens is that the string scale behaves exponentially. Okay, remember that S is 1/GS. So then if you plug this back, since there is this logarithmic here, you just get that this goes exponentially. It's 1/√8, this canonically normalized scalar. Okay. So this makes more manifest the fact that when we go to weak coupling, the cutoff becomes parametrically smaller than the Planck scale, right? It's an exponential behavior in terms of the distance, in terms of the canonically normalized scalar. Okay? And this is happening because, yeah, all the string modes have a mass that behaves exponentially. Okay, here. Questions? Okay. I hope everybody is following. I'm going slowly. Yes.
The capital phi very large for the separation.
Yes. Yes, exactly. So the point is, so this is equal to log 1/GS. Okay, S was 1/GS. So precisely phi goes to infinity, right? As GS goes to 0, and therefore the cutoff goes to 0 in Planck units. Okay. Okay. Now, this behavior here that I just presented in the most basic, the simplest CFT we have from string theory, which is in 10 dimensions. It's something seems to be general in any background, okay, in which we put string theory, like in any type of compactification. So what I mean is that, so first of all, the fact that all these continuous parameters, right, are set by Bev of scalar fields is general. It's just that, I mean, if you have some, now we can put this 10-dimensional effective field theory in some background in which we have some compact space. So we compactify part of the space, and then we still have some non-compact space, like for instance Minkowski, or we could also do it in ADS. Okay, so the point is that we want to dimensionally reduce this 10D effective field theory to a lower dimensional effective field theory, hopefully to 4 dimensions, so we connect with the universe, but free to choose the dimensions. The point is that, yeah, like in lower dimensions, okay, still, I mean, we are gonna have a similar structure, okay, so that we still have now some Einstein term, now in d dimensions. Okay, so this is Minkowski in d dimensions. Okay, in space-time dimensions. You have the Einstein term, and then you might have many more scalars. In 10 dimensions, we only had one, but if you go down, of course, you're gonna have some general metric, d phi, dj, many other scalars, and then the rest of the couplings of your Lagrangian are gonna depend on these scalars, okay? And these scalars, okay, now you have a more complicated manifold, so we are gonna have, I mean, if we come from weakly coupled string theory, we still have the dilaton, but then we're gonna have many other geometric scalars that parameterize the volume and the shape of these compact dimensions, okay? Plus, we have moduli coming from the branes and localized objects, plus periodic scalars, okay? Actions, Wilson lines, and so on. But the point is that the continuous parameters, which will have a non-compact regime, I mean, they will only depend on the non-compact moduli, okay? But the story is the same. Like all continuous parameters are given by this. If you come from M theory, then you don't have this one. But apart from that, this is the same. Okay. So let me make another example, and then we extract a second lesson. So, well, maybe already, actually, let me erase this here. Okay, so we've seen this, and we've also seen that the cutoff becomes exponentially light in Planck units, okay? So with respect to the Planck scale. As the canonically normalized scalars goes to infinity. Okay, that's what we learned from that example. And that's what we are going to argue more in general. And let me already put 3, although I will argue a bit, I will argue this with examples. The reason why this cutoff is becoming exponentially right is because there are new degrees of freedom, okay? Like in this case, there are string modes, right? All the string oscillator modes of the string. That are becoming light in that limit, because there are, I will move this blackboard up now, infinitely many new states. With a mass that goes exponentially in this canonically normalized, okay, in the geodesic distance. Okay, good. Okay, so let me explain this here, right? So in this case, it's obvious that, as the string scale, right, is lower than the Planck scale, is because we have all the excitations of the strings that we have integrated out and now become light, so we need to consider them again. And that's why the FT is breaking down. Now, if I only had one field becoming light, you could always integrate it in and get a new quantum field theory coupled to gravity. That's fine, okay? But the reason why here local quantum field theory description is breaking down, right, is because we don't have only one. We get infinitely many. And in this particular case, actually, they also have higher spin. So we cannot have a local quantum field theory. Okay. So these are the 3 lessons, okay, which I'm going to show you now in other examples, that are precisely what is known the distance conjecture. Okay, so I will formulate it more carefully, but that's it. I mean, this is the statement behind the distance conjecture. Okay.
Could you
Yes.
repeat how we are getting the mass of the new states to be exponential?
Yeah, in this case, it's so I will show you now with other examples, which is less trivial. Here is because the mass is precisely the string scale, right? Like the first, I mean, like you're gonna have the whole radio trajectory, the whole excitation modes with some scale that is precisely this string scale, have a full tower. And so, yeah, it's becoming exponentially light. So in this case, alpha is 1 over the square root of 8. Okay? So I'm keeping these factors, even if it seems a bit boring, on purpose, because part of the goal of the lectures is to be very precise about how this is becoming light. Okay? So we are gonna, I'm gonna tell you, I mean, this is something that has been a lot of progress in the past 2 years. We now understand what is this coefficient in general. Okay, so, but we'll go little by little. Yes? Yeah, so this is part of what I reserved for the last day, but so this is like a very basic thing from string theory, like nobody's surprised, I mean, this is like about this, right? But if you think about it carefully, right? I mean, it's really telling you that the scale, right, at which QFT breaks down, it's much lower than the Planck scale if GS is very small, right? If the scalar is very, very large. So now you can wonder, okay, like if I make a model, right, in this regime, of course, it's gonna break down at some point. So it depends, right, which type of model. Like for instance, this can have, I will tell you, can have implications for inflation, in which you need sometimes very large field ranges, and that can imply that the cutoff goes down. So that's the idea, yeah. Yes.
There's a field which requires a bev. The value of that bev controls the breakdown of the EFT, right? This seems very particular. Why is this expected to be general?
Yes, so the question is, why is this expected to be general? That's what we're going to see in these lectures. I mean, so the way I'm taking it now is like I'm going to motivate it like from the basic of string theory and so on. So we'll study more complicated examples. Then you can say, okay, can I get a general proof for that? And we can get some proofs in concrete, like classes of compactifications. Like I can get a proof in Calabi-Yau compactifications, things like that. You can go beyond and say, okay, can I get a general proof regarding, like without talking about compactifications? That's what we are working now in the context of ADS-CFT. That one can try to get a proof that. And then you can say, okay, fine, but can I get an intuition why this has to happen? Like, forget about proof, like just understand why this happens. And there, we have some black hole arguments, preliminary black hole arguments, that I can also tell you at the very end, because otherwise it's too much now. Yes. So here, I mean, we'll see more with examples. So this is the first example we see, right? Here, we just have all the string modes. So here we have infinite many, right? String oscillators. So it's like you have, yeah, you quantize the string, that goes out to infinity. You cannot just stop. Like if you start including some, like you include the full string. Yes?
So given P is a field frame dependent statement, is there something more geometric I can say?
Yeah, so I will exactly. I'm gonna make one other example, and then I will formulate this more like geometrical in the scalar manifold, okay? Yeah. I mean, precisely many of the proofs we have from compactifications come from, yeah, formulating this as a mathematical thing, compactifications, and then using algebraic geometry and other things to prove it. Okay, so let me just maybe here Yes, I want to complicate a bit that example, and then I formulate this a bit more carefully. I mean, the reason why I'm starting with this, I know, like more simple examples, let's say, yes, string theory in 10 dimensions, and now we are just going to compactify 1 dimension, is because I want to show you that, how natural in the end is going to be this feature in the string theory. Okay, so for that, you cannot start with the complicated things. You need to go to the basics, understand what's going on and why it's happening. Okay, so let me complicate this a bit. So this was in 10 dimensions. Okay. So let me, just for concreteness, focus on type 2A. So type 2A had that effective field theory description in 10 dimensions. And then we are going to compactify. Okay, so we go to lower dimensions in a compact space with volume V in Planck units. Okay, so in this case in 10D Planck units. Okay, so this is dimensionless. Okay, so if you do that, as I said, I deleted, but I mean, we had originally some, right, Einstein term, and then from just Kaluza-Klein compactification of the Einstein term, okay, we have an Einstein term in lower dimensions plus a new scalar, at least. I mean, we can have more than one, but let me focus now on this scalar, which is the overall volume, okay, which sets the overall volume of the compact space. So if I'm compactifying a circle, I just have the radius, okay, that's the field I'm talking about. And this rho, indeed, it's related. I'm going to put, because as I said, I want to be very precise about all the factors and powers and everything. So you can relate the canonically normalized scalar, okay, that just has a flat metric, okay, in terms of the volume of the compactification by this, okay. Okay, so this would be the canonically normalized scalar, and this is the volume. And this d plus n minus 2, so d is the dimension of the lower dimensional theory. N is the number of dimensions with the compactify, so it's the dimensions of this volume, the compact space of dimension n. Okay. Well, and 2 is 2. That's easy. Okay, so in general, I always write so all the scalars are always written in Planck units, okay? But
so sorry, is d plus n just 10? Not in general.
yes.
Okay.
Yes, I just put it like this in general because then I will use it. I will use this formula for the other cases.
Started in a different hierarchy.
Yes, exactly, for other cases. Okay. So in general, if we come from from a capital D, which would be this d plus n in general, we compactify 2D dimensions. That's what we get. Okay. Good. And maybe even if I'm gonna then suppress it, maybe let me be clear about one thing. So here, this I'm writing in the lower dimensional Planck units. Okay, so the canonical normalized scalars are written in the lower dimensional Planck units. These volumes are written in the higher dimensional. Planck in the higher dimensional units. Sorry, so this is over kb. Okay. Why? Well, I don't know. Sometimes conventions are nightmare. But the whole point is that you always want to write the scalars of the UFT in the lower dimensional Planck units, and that's why you do this transformation. Okay. Good. Say.
After the integration
Yes, exactly. Yeah, here we compactify, okay? So we go from D to D, capital D to small d, okay? And I mean, we have the scalar parameterizing the volume of the internal dimension. I mean, just taking some homogeneous compactification, otherwise can be more difficult. And then you also have the graviphoton at least, okay? So these are like bases of Kaluza-Klein theory. Plus, I don't care about this part, okay? So these are the zero modes coming from this. Now, here, if we are coming from string theory, right, from the type 2A, we had already a dilaton, okay, that if we dimension reduce, we still have a dilaton in lower dimensions, but we get a new scalar, which is this volume, which parameterizes the volume. So in this case, we have like a 2D scalar manifold, okay, parameterized by the dilaton as before, and now we add this row. Okay, we have two scalars. That's it. As I said, can be more, but let me focus on this universal part. Okay, so now what is the cutoff of this theory? Okay, so let me repeat. We have taken type 2A in 10 dimensions, some string theory, we compactify to lower dimensions. Okay, so we put string theory on a background that has some compact space, and we write the effective field theory from the lower dimensional perspective. Okay, this is part of the action. All the parameters, everything again, are parameterized by these scalars, which is the dilaton on the volume. But of course, this is an effective field theory, so it's going to break down at some scale. Here I'm ignoring many higher derivative corrections and so on. So what is that scale in that case? Yes?
It's some power of the volume.
Yes, indeed. So some power of the volume and the dilaton. Okay. Yes.
There is fines action.
Yes, so I didn't put it here because this was just the Einstein term. So also here, originally we also had the dilaton. Okay, when compact, like from higher dimensions. So when reducing, we still have exactly that term here as well. Okay, and the point is when you go to Einstein frame, I mean, there might be some couplings that depend only on the volume, or only on the dilaton, or on both of them. Okay. Okay. Yes.
Could you explain why your dilaton and your rho, like, how do I see that as a 2D scalar manifold, or how do I see it as a manifold?
So yes. So it's just a manifold in the sense that, so I have the kinetic terms for the scalars. Maybe let me explain it here. Okay. So you might have different scalars in your effective field theory. You have a metric here, okay, for the kinetic term. This metric, I mean, like the space of vacuum expectation values for these scalars is what is called the scalar manifold, which is equipped with this metric coming from the kinetic term. Okay, so you can think of this as a space where the coordinates are the scalars. Okay, and then you have a metric here, which is just this metric, and this is the scalar manifold we are talking about. Okay. So from effective field theory perspective, yeah, it's like you take the kinetic terms and that defines some, like the vacuum expectation value defines some scalar manifold. From the string theory geometric perspective, these are, I mean, if they are massless, for instance, this is the modular space of the compactification. So it's the space of the formations of the compact space. And that's why, yeah, it's like some scalar manifold. It's good. I mean, it's fine you ask these questions because this is the basics for, I mean, this is important, okay, to understand the distance conjecture. So it should be clear, okay, all these concepts. Okay, so here I'm just saying it's two-dimensional in the sense that I have only these two scalars, okay, nothing more than that. And now the cutoff, okay, it's actually gonna depend on these two scalars. Now, there are, I mean, let me tell you what it is in some limits. So, for example, if the if phi, which is related to the string dilaton, becomes very large, okay, much larger than the volume, okay, what is the cutoff is still going to be the string scale, okay. So this is if, right, this dilaton becomes very large, let's say going to infinity, like let's put maybe very, very large in Planck units, okay? Because, I mean, it's going to happen the same thing, like if GS, right, if the string dilaton is very small, like have all the string modes excitations that become light, and that's going to be still the cutoff of the CFT. But if the volume rho becomes very large, okay, more than the dilaton, okay, so the volume becomes large in string units, this CFT is going to break down also in a different way. It's going to break down because of all the Kaluza-Klein excitations here that I'm neglecting. Okay, so here, right, in this effective field theory, you have all the Kaluza-Klein modes and the string modes both. Okay. Okay, so Kaluza-Klein, right? Everybody knows what's Kaluza-Klein in that sense? Fine? Okay. If not, you should say it now. Okay. Okay, so we have all the Kaluza-Klein copy excitations from compactifying. And if the volume becomes very large, the Kaluza-Klein scale, which was as 1 over the radius, becomes very small. And you have to include them in again, right? So in this case, actually, the cutoff at which QFT breaks down, okay, so taking the same definition, the cutoff at which a local quantum field theory description breaks down, it's actually the Planck scale of the higher dimensional theory. Okay, that's the scale in which QFT, cannot exist. You will find first the Kaluza-Klein scale, but that still has like a quantum field theory description in higher dimensions. But once you reach the Planck scale of the higher dimensional theory, which is below, so this in Planck D, let me be clear, which if we are coming from 10 dimensions is just the 10D Planck scale, okay? It relates to the lower dimensional Planck scale with a power of the volume, minus 1 over D minus 2, okay? So if the volume is very large, okay, this Planck scale, the higher scale, is lower than the lower dimensional Planck scale. Yes?
How do we see that the cutoff has to be some function of both phi and rho instead of just max of either one or the other, because there are no mixing terms?
Yeah, it's gonna be max in the end. So this is in general. In this case, it's whatever is lower. Okay. Yeah. Okay. This case is very highly supersymmetric, so we actually know the moduli space everywhere. So that's why I can answer that. In general, it might be more complicated what happens in the middle. But okay. Okay. Very good. So now this string scale, just because it will be useful later, we can also write everything in terms of the canonically normalized fields, as I did before. And then you can do it as an exercise if you want. Like here you would put GS to the 1/4 m Planck d dimensions times the volume, because we want to write it in the lower dimensional Planck units. Okay? And then if you just replace this expression here and the one we had for the dilaton, you get e to the minus, let me erase this here. I will make it now. So just copy this because I will use it. Minus n over d minus 2 rho. And here you get m Planck d e to the minus square root of n d plus n minus 2 d minus 2 times rho. Okay, so this is if phi goes to infinity. This is if rho goes to infinity. Okay, so as I said, I will use these factors at some point because I will collect all this information to get some general constraints. But the message right now is just that, again, it happens the same story. We have some cutoff that goes down exponentially in terms of the geodesic distance, like the canonically normalized fields, when we write it in lower dimensional Planck units. Okay, that's it. Good. And it's happening, as I said here, this occurs because we get infinitely many states. So if we are talking about the string scale, it's the string excitation modes. But if we are talking about the decompactification limit, right, we also have infinitely many Kaluza-Klein states. Okay, so either Kaluza-Klein or stream modes becoming light. Okay. So again, we have infinite tower, and the Kaluza-Klein mass, it's also some power of the volume, right? So again, it's going to have this exponential behavior, right, when you write in terms of the canonically normalized field. Yeah? Good. So the message is that this simple thing, like here, I mean, we see two types of new fields that arise, either string excitation modes or Kaluza-Klein copies. These two things are basically everything that arises also in all the complicated examples. Okay, it's not so obvious because sometimes to see that they are actually Kaluza-Klein modes or stream modes, you need to go to some dual frame. Like maybe originally they correspond to wrapping branes or other things, but there's always some dual frame in which they look like this. So that's why I'm doing these particular examples. We'll see this in more detail tomorrow. Mm-hmm. Any other question? Okay, so just to finish, in the last 10 minutes, let's formulate this a bit better. Okay, so distance conjecture is basically promoting this feature that we observe in our string compactifications to a general feature of quantum gravity. So it says, given an effective field theory weakly coupled to gravity, so that we have, in case it was not clear, when I say kappa square, okay, is 1 over the m Planck square. Okay. So if we have Einstein term plus many scalars parameterizing my scalar manifold, there should be an infinite tower of states with a mass that behaves exponentially in terms of this geodesic distance. You compute with the kinetic term metric. So as long as, as this geodesic distance goes to infinity. Okay. Okay, so that the cutoff, the EFT breaks down at a scale lambda that in Planck units goes to 0 as well, in the same way. Okay. This is hard. Wait a second. so that you can see this part here. Okay. What is the origin of, sorry?
So, yeah, you're measuring distances, right? So you're measuring with respect to something.
The scalar manifold?
Yeah.
So it's like if it's part of the definition. Like you start with that effective field theory. You check what are the scalar fields that you have.
Yeah.
That defines some scalar manifold.
Yeah.
And then if you have non-compact directions in this scalar manifold, okay. Let me make a picture. So the idea is that I mean, you may have some scalar manifold, okay, and then you can have some cusps in the sense that you have some infinite non-compact manifold, so you have some limit in which the geodesic distance goes to infinity. So this is what is called an infinite distance singularity in the manifold, which is defined by the fact that any path approaching the singularity has infinite length. Okay, so if you have these non-compact directions, the message is that as if we start with an EFT defined at some random point, okay, let's say, and if we move, okay, we consider now an effective field theory defined at another point that are separated by a geodesic distance delta phi, the theory here must have this tower, okay, of states that decay, I mean, whose mass differs from the original one by this exponential behavior on the distance between the 2 points. And this is a behavior that becomes manifest as you make this delta phi parametrically large. Okay, so as you are approaching one of these infinite distance limits.
So it's like a relative thing, like.
It's a relative thing, exactly.
And at this point, what you're presenting, like, there's nothing like stabilizing these steps.
No, so.
It's still massless.
Yeah, so sorry, I'm not repeating. So he's asking whether I'm saying something about stabilizing the scalars. Do they need to be massless, right? So the point is that this, okay. So there are two options here, right? Either, so if we consider, I mean, we could have a potential for the scalars, right? So either it's a moduli space, right, in the sense that the potential, right, for these scalars is 0. So that if you want, potential is just some constant V naught, okay? So here we can have two options, Minkowski or radius. These are the notions the examples we have so far from string theory when you have a full moduli space because we need supersymmetry. So this, when this is moduli space, okay? Or the other option is that there's a potential. And then you could think of two options when you go to phi going to infinity. Either the potential blows up, or the potential goes to this 0 or this constant. Okay. If we have this case, then there is no infinite distance limit really within the effective field theory. So this does not apply. Okay, so here, no infinite distance limit to talk about. Okay, because the potential is blowing up, so we are not really, we can never approach, okay, the infinite distance limit. But if the potential goes to 0, okay, this is not a moduli space, right, because I have a potential. But this still applies, okay? In principle, these are for pseudo-moduli spaces in this sense, okay, which the vacuum energy becomes smaller and smaller as phi goes to infinity. Okay, so here, principle is fine. And the reason, I mean, last day, but the point, think of the Kaluza-Klein compactification. Even if I give some mass to the radius of to the compact space and I stabilize it, the existence of the Kaluza-Klein tower is still there, right? It does not depend on whether you stabilize the radius or not. like an intrinsic property of the fact that if you decompactify, you have all these Kaluza-Klein copies. And actually, the exponential rate doesn't change either if you go to the infinite distance limit. In any case, like for the today, well, like the first 3 days, like today I already did it because it was very supersymmetric, and tomorrow and the day after, we'll focus on this case, okay? So we'll focus on moduli spaces because there we have a lot of supersymmetry. Well, a lot. We have some supersymmetry. We have actually very well understanding of the geometry of all these moduli spaces. We can be very concrete and so on. But the last day, we'll come back to this. Here we have examples in 4n=1 or in non-supersymmetric, literally non-supersymmetric string theories, which everything still works the same way. And here is where we will also have more implications for phenomenology, right? Because in the end, if we want to connect this with the universe, it's interesting to understand, yeah, if it still works, no? Even if we have some scalar potential, no? The scalars are not completely massless. And this will be also related to, I mean, the tower will have also an impact on the potential, on accelerated expansion, many things. This answer the question?
So these files in the rows that you introduced here, they both have no.
Exactly. So the ones I introduced there, these were toroidal compactifications from string theory, so we were in this case.
Great, thanks. But does that make sense to draw your pictures with the manifold and everything if anyway these just fluctuate because they're magnets?
Yeah, that's why I say, like, this is much easier to define,
Okay,
right?
Yeah.
Here, it makes sense. You can still draw this type of pictures up to some energy scale. You can choose the cutoff and say, okay, let me consider what are the scalars that are lighter than this. And then you have to draw, right, what is the potential here? And then you have to ask, okay, if I go infinitely far away, like, how does it look? That's still smaller than the cutoff so that I can still approach it and so on, okay? And yeah, as I said, like, we'll see that one of the features in string theory is that if you really go asymptotically, the potential actually goes to 0, so it becomes smaller and smaller, always. And you can also understand this because of the tower. Yes?
So the statement of the conjecture would, like, it's telling us that there will be night modes if we, like, is it telling us something about the cutoff also? Because that's what we started with, right?
Uh-huh. Yes.
Something about the cutoff.
Yes, exactly. So let me be clear. So the point is that here, because it's an infinite tower of states, you have there's no, at some point, there is no QFT description that you can write. So that's why the cutoff, I mean, we'll see how to define it. So in these cases, was either the string scale or the Planck scale, right? In general, it's also going to behave exponentially. Okay, this distance. And the relation between this factor here and that factor alpha there, it depends on the nature, the microscopic nature of the tower. So whenever it's Kaluza-Klein tower, we can fix these factors, and it's a specific thing. Whenever it's string towers, we can fix the factor, will be a specific thing. So this will quantify better tomorrow. And so that's from the top-down perspective, let's say. And also something, for instance, one of the interplays that we are having with this matrix bootstrap is that this is also a very natural question from this matrix bootstrap. What is this cutoff, right, at which QFT breaks down? In general, from bottom up, this is known as the species scale because you have infinitely many fields, infinitely many spaces, and so on. And there's a way also to reach the same powers and everything from bottom up. And actually, I think you had lectures from Simon last week, right? They actually has some nice papers in which they are bootstrapping, like what is this cutoff? And they are finding a perfect match with what we find from string theory, like from top down, okay? So in general, yeah, like I will also tell you how to determine this from bottom up, like given an AFT. But this is one of the points in which like the top down and bottom up are, yeah, helping each other, let's say. Okay, I finished here. I don't know if there is another question. We should stop. Probably more than enough.
Yeah.
Yeah, so let's do, since we're a few minutes over, let's do more questions after the break. I just want to remind you about tomorrow. We have our barbecue. It's at 6 o'clock in another part of the UMC where you have lunch. So I'm thinking most of you won't want to go back to Willville between 5 o'clock lecture and that. So bring your, I was going to reach for my name tag and I don't have it. Bring your name tag, bring your ID for both of those, like for the reception, so that you just have them, and then that'll be 6 o'clock tomorrow. See.
Yeah, of course.
So if I have some kind of like quintessence like setup where the universe expands and the data rose to large value, does this mean that even if I have a large universe, I still have stringy physics?
In a sense, yeah. So the interest, yes, of course.